since you have the metric tensor GRJ, we have geodesics. Geodesics satisfy some second order differential equation. And it's actually, the way to build is completely the same as you do for the Riemannian metric, if you know. So you go from, you have GIJ, then you build up Christoffel symbols, and then look for the second order equation that involves Christoffel symbols. So, of course, I mean, GIJ now is funny because it has this minus direction, but otherwise these equations are the same as second order equations, and they have a solution, and we assume that, well, actually, we don't need to assume that that geodesics continue to infinity, but let's assume it is the case. For our inverse problem, it's not necessary because it's not really. I mean, there's discussions in cosmology whether this is the case for our space-time. So there you have geodesics, right? Geodesics. And they are defined by the initial position, x0, and the initial direction. So, and then geodesics goes that way. And that will be denoted by gamma x0 psi 0. I put it S. Then gradually they put in T because time will be xn, something like that. No. So this is geodesic. And you know that from that if you go along geodesics, and this is so this geodesics, and that will be the velocity in this point, right? So it is gamma dot with respect to S of x0, psi 0, and S. That's velocity. And the same as Riemannian geometry, this thing is preserved at the point. Let me also call it x of S just for the brevity. Is constant. Okay, so the length, you can say this is the square of the length. If you have a vector attached to the point x, psi x, right? And this is point x. Then you would say that this guy is the square of the length. The only point the square can be negative, right? If it's time-like direction. But still it's a length vector. So let's call this at the moment. So this length of the velocity vector on geodesic is preserved. That means if you initially take psi 0 to be time-like, then it remains time-like all the time, because this will be negative. If you send a light ray, so this is 0, psi 0 is the light direction, it will be light direction all the time. So photons propagate along the light rays, light geodesics. Okay? And the mass bodies in the free space, so for example, you and me, we go along time-like geodesics, right? In vacuum, of course, if yes. Okay? So, and the larger the mass, the more it's like time. Basically, the larger the mass, the more your inertia, and less you move in space. Okay? So, we can look for, not only for geodesics has some curves, right? Smooth curves of S. You can look for piecewise smooth curve of S. So, that's mu of S, that is mu1 in local coordinates. Mu n plus 1 is a piecewise smooth. Okay, something like that. So it goes this way, then it changes, probably changes again, as usual. So you look for piecewise smooth curve, and you see that this curve is mu s is time-like. Mu s is time-like. If mu dot of S is time-like for any S, and so on. Like it is light-like when it is mu dot of S is light-like for all S. It's causal when it is mu dot of S is causal. It means either light-like or time-like. We should be careful because when we come to this breaking point, so there are two velocity vectors here and here, right? assume they're both time-like. We also require that you don't change the direction. So say if this is future direction, this also you don't go that way, right? You continuously go into future, go into past. So that this is acceptable piecewise smooth curves. That are piecewise smooth, they preserve being time-like or causal, and when they break, they still stay the same future cone. Okay, then if I have 2 points, P and Q in the space-time, okay, well, sometimes I say not Lorentz manifold, but space-time for obvious reasons, right? P and Q in the space-time, and if there is a time-like curve, I try to put the flight lines at 45 degrees, and when it is more vertical, it's time-like, and less vertical, it's space-like. So, to be honest, we will never ever bother about space-like curves because they're not physical. So that's my. You see, I try to show that it's time-like. So, if we say that P is much less than Q, if there exists time-like piecewise smooth curve, more or less, from P to Q. And we say that P is less than Q if there exists a causal. That means that we can go with the velocity of light. Causal piecewise curve more or less from P to Q. And also P is not Q. Okay.
What means positive timeline?
Yes, some people say it's positive. Well, I mean, in this case, right, it's positive. So this is, it's future looking.
So because you make a choice.
Yes. If you go from Q to P, you go at the same time like curve, but now it's past looking. So, okay. So, physically, if P is less than Q, that means that event P can affect event Q, right? Because we have the proper causal curve. Also, the last thing is P is less or equal than Q means that either P is less than Q or just P equal to Q. So in Minkowski space, if this is P, then all the points that are so if I draw here the positive looking light cone, then all the points that sit in here inside this cone will be satisfied that P is less than Q, right? Because there is this time-like curve, and if it's sitting about all that sit on the closed corner, they're causal, right? That is, by the way, not trivial thing because, well, more or less, now we introduce the corresponding objects. So, I plus of P, these are all Q's, such that P is less than Q. Okay. And J, you can put minus, of course, here. Minus means that you have opposite direction, right? That P is more than Q. J plus of P is all Q's such that P is less or equal than Q. So in this case, I plus is the open cone and J plus is the closed cone, right? Actually, I plus is always open. This is an open set. But J plus is not necessarily closed, and therefore it's not necessarily the closure of I plus. In this case, of course, J plus is just the closure of I plus, right? But this is not generally the case. J plus cannot be even closed. For example, if I take from my manifold, I look in here, but I subtract this point, then all that is subtracted. Because my geodesic can go through this point. I take it out of the manifold. Manifold stops there. So geodesic stops there. It comes from here, but this point is taken out, so I can go further. So in this case, J plus is not open because I take away the whole ring. It's not closed. I take away the whole ring. That is bad case. I mean, it's bad case from anesthesists believe that's not the case. Actually, we put some extra condition, and this extra condition is the following. Now we introduce these notions, and of course you can put here minus, so it will be that way. And what is the condition? Well, I denote by I, so let now P will be less than Q. And denote by I, PQ, that is the intersection of I, well, it should be here like that. I, P is less, I plus of P intersecting with I minus of P. So it's picture like that. So this is my P, that's my Q, there's the forward-looking cone for I, for P, this is backward-looking cone for Q, and this is this. And the same, of course, is J. JPQ is J plus of P intersected with J minus of P. And now important definition. Lorentz manifold for space-time G is globally hyperbolic. If first there are no closed causal curves. That means you cannot leave and then return to your childhood, unfortunately. Okay? And second, for any P less or equal than Q, J of PQ is a compact. And we will deal with globally hyperbolic Lorentz manifolds. Okay? So this is very, very somehow. If it's not true, we can write a lot of fantastic novels. How you live and then born again from the same parents in the same place, right? Actually, this is very much corresponding to the Hindu mythology. You are reborn. And this is sort of more delicate thing. In particular, this implies that J plus of P is actually closure of I plus of P. So it's closed, and actually it's the closure of I plus. So this case, remember, when we take away a point, is excluded. It's no more globally hyperbolic. Okay. What do we do next? Next, we introduce another important notion. You know, in the Riemannian manifold, we have such a nice thing that's called the distance, right? And we used it in our construction. And now we want to do something similar to distance, but sometimes the length of the vector, the square of the length is negative, sometimes it's positive, sometimes it's 0. So what shall we do? So actually we introduce distance only along the points that satisfy this condition. When Q is more than P or P less than Q, then we can introduce the distance from P to Q. But we can't introduce distance from Q to P. You see? Because it looks opposite around. So it's only for those points. Actually, this distance function is called time separation function, but it's sort of version of distance. Time separation. Function, and it's denoted tau of P and Q, and we should require, well, I mean, actually it's anything, but it's not symmetric. How it is defined? The first case, when P is less than Q, tau PQ is actually supreme of all the curves mu between P and Q. So between 0 and sort of 0 to 1. So it's a 0, 1, and when we at 0 and P, when at 1 it's on Q, and this should be causal future looking. Causal future looking. Because it's causal, the square is non-positive. So, but you know, the length is the square root of gij dxi dxj. So therefore we need to change sign to keep possible. So that's what we get here. Minus gij of x of s, x dot I of s, x dot j of s, ds. And this from 0 to 1. So initial point 0 was P, final point was 1, and we take now supremum for all the causal curves. So something like that, right? So we can go this way, or we can go that way, and we take supremum. Do you feel the difference? It's now not infinite, it's supremum. Right? So this is the case when P is less than, actually when P is strictly less than. In another case, otherwise, tau PQ is 0. Okay.
That's supreme.
Huh?
Why does it make sense to take a thing of a supremum? So if you just took the Minkowski,
Yes.
in that case the supremum is.
Whoa, that's a good question. So let's look why it is not infinite but supremum. So let's look at Minkowski. Let's look two-dimensional Minkowski. Of course, they're the same. So this is time and this is x. And so I start from 0, and of course all, cone is this cone, and I take this point, right? And then what I do this way. I can achieve any point inside this cone by like curves. So the infinite will be 0. There is no point. It's always 0. So it has no meaning. Well,
So why is it because the norm in that metric?
Yeah. So I go that way, right? This is 0 here and 0 here, and I come to this point.
It's that norm.
Okay.
Also, now you parameterize your curve at 0, 1. Does that affect the?
No, because it's as the distance it's invariant with respect to change of variable, change of reparameterization. You can move along the same curve with different speed, make from s to tau of t of s,
right,
and it will be the same.
So in Minkowski space, what would it be?
That's good stuff. Let me answer it. That's actually here. So there is. Once again, what is it? The H is only when we are inside this J. So it means that Q belongs to J plus of P, right? In this case. So a lemma for any Q belonging to J plus of P, there exists a a causal, future looking, I won't pronounce future looking because automatically here, a causal geodesic, gamma PQ of S, again, at S equal to 0 here, S equal to 1 on Q, such that tau PQ is equal to the integral from 0 to 1 G gamma dot minus ds. I don't want to put I, j, so, okay? So in this case, so we are here, so we just a straight line. Okay? This is time lag. Okay? In particular, on the boundary, that will be the light line geodesic. So, you see, that is why you see this supremum corresponds to infimum. We know that in Riemannian geometry there is always the shortest geodesic. And this is the shortest curve between 2 points. In Lorentzian geometry there is always the longest geodesic, and that is the longest curve between points. Okay? So, basically, when you go for Riemannian to Lorentzian, you say no to everything. For example, you know that in Riemannian geometry, dxy plus dyz is more than dxz. What is Lorentzian geometry? Because everything's opposite round. So if you have that p is less than q and it's less than whatever pq, say r. It's no more boundary distance function. Then you have the tau pq plus tau qr is less than tau tr. So it's a reverse triangular inequality. And the problem is the same for now. You look for now you look for the supremum. And if this is only when you go this way, it's only part of possible causal curves. Okay?
What about Minkowski geometry then? So P took as a distance between P and Q, right?
There's no distance. It's time separation.
I don't mean the distance in the R4 in the standard sense, though. No?
No, it's not.
No, it's not.
What is distance R4 in standard set? There is no distance because it's a negative something negative. No.
What's the value of that quantity in Minkowski? Suppose I had P and Q. It's not the length of that line segment, correct? If I did Minkowski for that,
yes,
and I put those P and Q there,
yes,
what is the value of that distance?
Well, that is the vector. So there's the vector. So it's that sort of we have less than 0. This is has coordinates q1, q4, right? So and what will be that? That will be exactly this.
So the value of norm of that in the Minkowski.
Sorry, it's q4. It is 4. q4 squared minus sum qi squared from 1 to 3.
Minkowski no.
Yes. It's minus.
Okay.
Because otherwise it will be squared. It's still geometrically. But let's see how funny things can be. Do you remember that well, of course in Minkowski this cone of future is just this one, j plus j. But what about this our other example? Remember there was an example that was this one. I need to draw it large. So this is circle by R. So that is our Minkowski space. It's two-dimensional, right? And 2 is S1 by R. So this is time and X is so what will be J plus for this point? Well, it's first you just go in direction 1 in T, in direction 1 in X, so it goes like that. But then when you come, so this is this one, and then it continues, and then it comes here, and this moment, after that it will hold cylinder. After pi, you'll cover all possible x points. And so after time, no, it's not time, but actually time, you can say it's time pi. This all cylinder above belongs to J plus. Okay? So you go light. So the projection of your light will be just these circles, and you go simultaneously the same speed this time. So you go this way, and if you go that way, after pi you meet, and after that you cover the whole possible circles. So after that, the whole upper cylinder is in J plus of P. Okay? Right. So it's quite interesting case. I think I'm almost the last thing I need to introduce, and this is also a good example. We can look for the light cone. Remember, we had the light cone in the tangential plane. These are all light directions. But now we look for the geodesics that start in the light direction and continue until infinity. So this will be L plus at the point P. These are all points x of the form gamma p psi of S, where psi is light belongs to L plus at the point P. So this means that the vector, the direction is in light cone. L from light. And the difference here is this beautiful L. Now we're in the space, because now we're moving in the space along the light geodesic. And S is positive. Actually, it's strictly more than 0. To close, you need to end the P point. So it's the cone, and then you close the P point, right? So this picture, what will be the light this L plus? Well, this will be these sort of spirals, right? This spiral and this spiral and that spiral. That will be L plus. Agree? And in Minkowski, just this cone itself. You go straight and you continue straight. So what is this L plus? That's basically the following one, physically. You send a photon or a gravitational wave from the point P in the direction psi. Photons and gravitational wave propagate with the speed of light. And that's how they propagate through the space-time. Okay? So if we are sitting with our telescope and we see a light from some star, that means that the photon from the star is going along the light ray and comes to us. Okay? Now, assume that there is a supernova that appears. It's a blow up. There is an event, and before an event, it sends you rays in all directions. So this blow up of supernova, and some moment you fix it, and after that you see this supernova. There is so this is you or me. Especially I have quite a heavy mass, so therefore my world line is a time-like geodesic. So that is Professor Kurylev. Okay, and he's looking at, and there is somewhere here a supernova. This is the time when it appears, produces blow up, and then actually that will be it's also some time-like curve of supernova. But that's a starting point. And this starting point, and it continues to produce these light rays, right? And these light rays propagate, and at some moment I find this is a supernova. So, and I can find this starting point. Namely, I can neglect these points and find out when this light ray comes from this point event in the space-time. The same story, so I can not find the whole world line of the supernova, but for the starting point when the light comes. It may be, by the way, that because of complicated geometry, if I've heard about caustics and things like that. Oh, for example, in this picture. For example, I'm sitting here, and then there are two light rays that come here, this way and that way, right? And they come at the same time. But if I stay in here, assume that this is my world line. Then at first will come the light ray from here, and then comes the light ray from here. And still, it will be me who registers the light from this point later. Okay? So that's what astronomers do. And they really see that because of the curvature of the space-time, it may be that the same stuff of the same time, that means from the same event, produce a light cone, but some lights go long trajectory, come later. And I think the record now is like 476 days. They find stars that so they see the light from these stars, and then in 476 late days, they see the light from the same star that was immense. What you do with light? You emanate from the same way, but in a different way. There are beautiful pictures like Einstein crosses, Einstein circles that are made from all these events that light can go. So it's not the same point because time changes, but it's the same person, me, who registers the same stuff. And I registered many times, and what I saw can be crosses, double stars, but they came from the same event. Okay? So we need to be careful. Look at this picture. I register this event here, and then I register this event here, twice. But what are all these points? So, and now they're coming closer to what is the formulation of the inverse problem. So, assume that we make measurements. There are a whole bunch of observatories that make light measurements. And in the space-time, we have a major time-like curve. Maybe geodesics or not geodesics, depends on if somebody hits me, then I need to break, right? I hope it won't happen, but still. So there are time-like curve. And then that's called mu of s. And this is s equal to -1, s equal to 1, and this is some p plus, that is p minus, s minus, and p plus, that is mu of s plus. So this is my working time when I make my observations. And I have a whole bunch of friends, and they make observations in some vicinity u of this time-like curve. So I call it Q. And then there appears some quasar. By the way, it's not only supernovas. There are other stars when astronomers can say that this light comes to the same event. For example, quasars, because they have frequency. And by frequency, they can find, these two events correspond, these two lights that come different times to correspond to the same event. Okay? So there is a point here, and produce light cone. And maybe it comes with later here, yeah? So this is L plus. And for this, and we measure light when it comes. So we know Tu of Q, this is with light cone of Q intercepted with our U. Okay, there's the observation of supernova or quasar or whichever, pulsar, and we find out when light comes or when gravitational wave comes. Though gravitational wave people cannot yet register, but they also propagate with the speed of light. Okay. Now we do the following trick. So colors. We look for I minus of P plus, so past looking cone, time cone from P plus, and we look for J minus of P minus, and we look for this set. So this is this set, right? I think I need to use too many notations. So this is my curve. This is P plus. This is P minus. And this is this. Okay. So this is I minus of P plus. So that minus G minus of P minus. Now it's open, right? Because it's open and it's subtract closed. And we assume that there is a region V that sits in here, and this is open and relatively compact. Relatively compact means when you close it, you get a compact region, and this region is full of supernovas. That's your register. And for any Q belonging to this V, or actually belonging, well, V is enough, but you can look V closure. We have, or we measure this PU of Q. Now Q belongs to V. So your region V is densely full of supernovas or quasars. Okay? And because they're supernovas or quasars, you can say, oh, this light came from this, oh, this light and this light came from different sources. Right? That is the idea. Astronomers know that this light this light and this light come from the same source, and this light and that light come from different sources. So that's we know. So we know actually these sets for different Qs. Okay? And then the main result is the following. I put it here with a question mark because, of course, it's sort of hand-waving. I mean, it's not very precise. Let the know G on U, where we make measurements, up to conformal transformation, up to a conformal pattern. I'll later bit explain what is that, please. Let we measure this set PUQ, this intersection of the light column from Q with the set where we make measurements U, for any Q, for all Qs belonging to V. And V is relatively compact and lies in this thing. This determine topology. I just to show that it's the same procedure as earlier. Topology and differential structure of V. Remember, it was our first step, that was our second step, correct? And the first step is slightly weaker. And geometry is metric tensor, and metric G on V up to a conformal pattern. Now, once again, we assume that our Lorentzian manifold of space-time is time-oriented and globally hyperbolic. What does it mean after conformal pattern? Well, two metrics are conformally equivalent, metric G1 and G2, they are conformally equivalent. So if, say, g2 of x is some positive function, smooth positive function g1 of x. And because it's positive, you can always write it this way. Yeah? Take 1/2 of the log. So then these two matrices are conformally equivalent. And then we speak about conformal differentials. That's differentials that when you look metric in this corresponding coordinates, that is this conformal factor that you don't know presumably, right? This f is unknown. It's for any f. This is correct. Well, you cannot do anything better. You see, it's almost like our previous 1 to 3, except for the case 3, it's not the metric, but metric conformal factor. There's no way out, because what we're looking for the light trace, right? And if you have vector gxi that is like, so we have the g1ij of x psi, sorry, so it's round. It's a vector, so it should be downstairs. So you have g1 ij psi I psi j is 0, then of course this is the same as e to the power 2f g1 ij, yes, psi I psi j equals to 0, but this is psi g2. Conformal transformation doesn't change light cones. Moreover, not only tangential light cones, but also this applies. You can say, well, there are two understandings. First of all, the point is the following, that the same with pluses. If this is, say, negative, then this is also negative. You multiply negative number by positive, you get still negative. Therefore, all causal curves with respect to G1 are the same as causal curves with respect to G2. And therefore, all these curves are the same, and the boundary is the same. So you won't distinguish between them, it's just sitting on the boundary, right? So that's the best possible you can achieve. So our goal is to prove this theorem. Sometimes you can do better. Sometimes you can do better. You cannot take into account conformal transformations. And this is the following case. Let me still formulate it. Assume that you really know the magic in you, coloring. If we know G in U, not only up to the conformal factor, and G in V is Ricci flat. Now, those who don't know what is Ricci flat, just enjoy. And any component of V intersects U, then we identify G on V as well. Conformal factor is not there. Because I didn't say that V is so if U was like that, that's not a proper picture because now V and U do not intersect. So I need that my U is something like that, right? Then it will be this condition, but also should be Ricci flat. Ricci flat is actually physically meaningful. You know that Ricci tensor defines Einstein tensor. And the Einstein equation says that Einstein tensor is the metric stress energy tensor. So it's geometry, and the right is physics. So when stress energy tensor is 0, it's vacuum. There are no mass there, right? So when they are in vacuum, then stress energy tensor is 0. Then Einstein tensor is 0. Einstein tensor 0 is equivalent to Ricci tensor. It's 0, and flat means 0, right? So that means physically, this means that V is vacuum. Right? Then we can find this way. Okay. So that now let us prove this theorem. Actually, well, the theorem is actually in the form of uniqueness. You still have two universes, two Lorentzian space-times, M1 and M2, and there are two me's who made this. I mean, this is me in one universe, there is me in the second universe. Again, I think it's a very Indian idea. There are many universes, right? And we have measurements, and there is V1 and V2 in the other universe, and then there is a transformation from my U1 into U2. That is conformal diffeomorphism, and all these P's, they're transformed from one universe to the other. Then there's basically the same universe up to the conformal diffeomorphism. Okay. So, but it's sort of constructed procedure almost, like it was in Riemannian case. Therefore, I formulate it this way. What did we do in Riemannian case? And what I say is a very good thing to look for geometry. Is to describe our manifold as a set of functions, right? It was this distance function on the boundary. So what it is? So the first, we want to introduce a set of functions that are associated with this PU of Q's. So each Q will give its own set of functions, its own function. Like in the remaining case, x inside give you the distance function to the boundary. Another x is another distance function. So one Q will give you one function, another Q gives you other function. And then on this set of functions, you introduce topology that you actually not you extract from it topology that is equivalent to topology of V, then extract from the differential structure, and then extract G. As in the same strategy, what will be the set of functions? Well, and the point is the following. As I say, well, we make, in this U, we make observations, light observation. What does it mean by that? There is where is the nearest astrophysical laboratory here? Somebody there makes observation, somebody in Pulko makes observation. So what goes on is the following, that you can imagine, and that's actually what is done, or you can do it mathematically. Let's forget for a moment about V. So this is my observatory. So it is P minus P plus, and that corresponds to S equal to 1 and S equal to minus 1. And then there is a family alpha belonging to A of curves that will be all time-like curves, and that depends upon alpha. So mu alpha of S that depends smoothly. Well, that depends smoothly about S. That's always, but also that depends continuously on alpha. So you change alpha, you change this time-like curve slightly. So that's something like that, right? And altogether, if you take the union of this mu alpha of S, and I put it from minus 1 to 1, the open guys, and alpha belongs to A, that will be our U. And if you take the closure, mu alpha of minus 1, 1, that will be the closure of U. Okay, so somehow you represent your U as the union of the passes. For example, what we can do, we can go to this point S minus 1, and we assume for beginning that this mu 0 of S, that is my world line, is gamma x0 psi 0 of S. And at S equals minus 1, I'm here. And then you take alpha to be x and psi close to x0 psi 0. So, for example, take the point here and take the direction close to this one, and you send this jet. And so x and psi and form open neighborhood of x0 psi 0. So our A are all at 0, x and psi that are close to the x0 and psi 0. We should time-like geodesics from close points and close directions. Then, of course, when we take the union with an open set, and when we take, now we should, when we close the set of directional points, so we get a closed set. Okay? And that corresponds exactly to the case we have astronomical observatories. Okay? So, a crucial point that these guys are mu alpha of S is continuous with respect to alpha and on A closure and smooth in S. Again, it will turn out that what we are aiming at, we will be able to associate with any Q in V, actually in V bar, a continuous function f q of alpha. So that's what I'm going to do sometime next lecture. And so you see, that's the point. You have Q, I build up a function on A. We have a point inside, we build a function on the boundary. And then we get a set of functions. So we get f of v, or if you wish f of v bar, this is the set of all f q of alpha when q belongs to v. And that is belongs to C of A bar. By the way, A closure should be compact. Like in that example, A closure is composite. Put here dn and put here R of n. Yes, sort of very, very similar. Before going, I think I have 5 minutes, right? Because I start like 35. What will be this? So you see, it's function of alpha. So what we do is the following thing. Let me define this function. No, it's not good. Can you believe that?
Yeah.
Oh, maybe I still have here. So let us consider the time separation function along any curve mu alpha. So we take curve mu alpha of S, and we look for the time separation function. So we take it, remember, Q is now fixed, and we look at tau of Q mu alpha of S. Now what we know, if A is small, means that in that case we take x is relatively pretty close to x0 and the direction psi pretty close to psi 0, then because we are sitting, you remember we are sitting in this our Q is here in between these two lines, then we'll have that then tau Q of mu alpha of -1 will be 0. Well, there is no, if Q is here, there is no time like curve from Q to the mu minus 1, playing alpha. And tau Q of mu alpha of 1 is strictly positive. Again, because we are, 1 is here and the point is here. So along this line we can go that way, right? So that will be the curve. It's a light line, and then along the time line, so tau will be positive. Okay? So that is our object. We look for the time separation function along the world line of each of these observatories. And what are the properties of this time separation function we'll discuss Monday?
Yeah.
What time Monday?
I'll let you know. It has to...
Let me know in advance, because I probably won't cover the first 2 hours.
No, if at all, it will be in the afternoon.
Instead of Cliff, right?
Cliff.
Yeah. So it will be the last one, I guess. Yeah. So it will be the last one on Monday. This is the last talk. You suffered a lot. Thank you very much. Questions?
So I'm trying to understand, I think you said this already. So all your neighbors are telling, oh, I saw something, or
yes.
I didn't saw something.
Yeah.
From that, you're just trying to get to that.
Yes. And also topology, and also instructional structure. Not something, you see the same, because we know that this quadrant has this frequency, and the other quadrant has different frequency. Therefore, we can distinguish one from the other.
Right, so you're saying, oh, I saw this one,
yes.
or I
now I see the same guy, right?
And of course, you tell them the time also. I saw him yesterday or today.
Oh, yes, right. Yes.
And so when you see something, don't you get some sort of distance or something?
I don't know what is distance.
Right,
I know it's time separation,
right,
but I can't measure it. I can't measure it.
So when you say I see it, what does that mean?
I know PU of Q. When the light from this star comes into my world, they come into this room. This room is actually not a point, we also move in time, right? And we see, into this point of our room, light came this time. And then light from it came to some probably distant point, some other room at that time. And then you say, oh, that's from this class, they have this fancy name, this class. Something many letters and numbers. But forget about it, it's mathematical problem. It's mathematical problem. I'm not astrologist,
No, I know.
Otherwise I will not,
So I'm trying
the amount of money will be probably multiplied by 100.
And all these particles are traveling with the speed of light.
Yes.